Welcome to This Explainer. Have you ever actually wondered how an instant cold pack just gets freezing cold out of nowhere? Well, today we're throwing on our lab coats and playing Energy Detective. Based on a classic university chemistry lab manual, we're going to track down the invisible transfer of heat. It's this absolutely fascinating dive into thermodynamics where we'll figure out exactly how scientists capture, measure, and crunch the numbers on the energy released or absorbed when chemicals dissolve. So let's get into it because we are literally about to make the invisible completely visible.
Okay, let's dive into this. Think about it. When you stir table salt into a glass of water, it vanishes, right? But what about the energy? Where does the heat actually go when chemicals dissolve into a liquid? Down at the microscopic level, these molecules are just violently colliding and tearing apart. But how do we possibly measure something that we can't even see? Well, the trick is we use a highly controlled environment to catch it right in the act. And today, we're going to learn exactly how to build that trap and force that heat to reveal all its secrets. So here's our lab syllabus for the day so you have a clear mental map of where we're going. 1. The rules of heat exchange. 2. Meet the calorimeter. 3. Testing acid, base, salt. And 4. Crunching the thermodynamic numbers.
All right, starting right off with Section 1, the rules of heat exchange. Now, before we mix a single thing together, we absolutely have to lay down the ground rules, the two fundamental laws of the universe that govern this whole experiment. First up is the principle of equal heat exchange. It's a beautifully simple rule. When one system exchanges heat with another, the exact amount of heat gained by one is perfectly equal to the amount lost by the other. It's just a one-to-one trade, nothing lost, just transferred. Second is the principle of inverse transformations. You can think of this like a perfect thermodynamic loop. If melting an ice cube takes a very specific amount of heat, while freezing that exact same water back into ice is going to release that exact same amount of heat.
So the crucial point is how these principles actually apply to our setup today. Whenever we talk about enthalpy, we're just talking about total heat energy. That's it. When a chemical breaks apart or dissolves, it's essentially doing the exact opposite of what it did when it formed. If forming it took energy, breaking it apart releases energy right into the water, heating it up. So think of our tiny beaker of water as a trap. During a reaction, all that heat doesn't just vanish, it transfers directly into the water. Our goal here is to catch every single joule of that heat so the entire equation perfectly balances out to zero.
Which brings us to Section 2, meet the calorimeter. Let's move to our actual toolkit and see how this builds out our experiment. The real star of the show here is the calorimeter itself, and it's backed up by a hot plate, a highly sensitive thermometer, a balance for precise weighing, a graduated cylinder, and an Erlenmeyer flask. And then we have our chemical suspects for the day: sulfuric acid, sodium hydroxide, sodium carbonate, and of course, our trusty solvent, distilled water. But wait, before we test any of those chemicals, we have to calibrate the calorimeter first. Why? Because the container itself is kind of like a heat thief. It absorbs some energy on its own, and we have to account for that. So first, we place exactly 100 milliliters of water into the calorimeter and measure its initial temperature. Next, we heat a totally separate 100 milliliters of water to exactly 60 degrees Celsius. Then, we pour that hot water into the calorimeter. And speed is absolutely critical here. We have to move fast so we don't lose any heat to the surrounding air. Finally, we shake it up well and measure the equilibrium temperature. By rapidly mixing the cold and hot water, we can figure out exactly how much heat the cup itself steals before we even introduce the chemicals.
All right, moving right along to Section 3, testing acid, base, salt.
So our first case study is a base. We start off by placing 100 milliliters of water into our trusty calorimeter and jotting down that initial temperature. Next up, we carefully weigh out approximately 2 grams of sodium hydroxide. Then we just toss that solid base in all at once and give it a shake. Now I want you to imagine those solid particles just violently breaking apart in the water. Ask yourself, where is all that energy going? We wait patiently for the reaction to hit its thermal equilibrium, and then boom, we record our final temperature.
Let's keep that rhythm going for our second case study, an acid. Once again, 100 milliliters of distilled water goes straight into the calorimeter, and we grab our initial temperature. Now, what's really interesting about this slide is the physical state of our chemical. We're not dropping in a solid powder this time. Instead, we're mixing 5 milliliters of a concentrated liquid, sulfuric acid, right into the water. We add it super carefully, shake it really well, wait for that thermodynamic equilibrium to settle in, and grab our new final temperature.
Third time's the charm. For our final case study, a complex salt, we're going to repeat that exact same protocol. 100 milliliters of water goes in so we can find our initial temperature. We weigh out roughly 2 grams of sodium carbonate decahydrate, we toss it all in at once, give it a really vigorous shake, let that energy transfer run its full course until it hits equilibrium, and we take the final temperature. And this brilliantly illustrates how keeping our method perfectly consistent allows us to expose the entirely unique thermal fingerprint of each distinct chemical.
And finally, we arrive at Section 4, crunching the thermodynamic numbers.
Okay, so we've gathered all of our data, and now we're at the final deductions phase, where we translate those temperature changes into actual measurable energy. To pull this off, we need a few very specific constants. We need the heat capacity of water, which basically just tells us how much energy it actually takes to heat up the liquid, and the unique molecular weight, or molar mass, of every chemical we used. By plugging these specific puzzle pieces into our formulas, we can finally calculate our final enthalpies of dissolution. We can state exactly how much energy was transferred in joules, in calories per gram, and in calories per mole.
So we've set up the trap, we've executed the reactions, and we've got the data in hand. You know, this exact math holds the answer to how we design everything from massive industrial power plants to those instant cold packs you have in your first aid kit. So look at your data. Did the water get hotter or did it get colder? Are your specific dissolution reactions endothermic, meaning they absorbed heat right out of the water, or are they exothermic, releasing heat into it? I challenge you to run the numbers and find out for yourself. Thanks so much for joining me on this explainer, and keep exploring the incredible invisible energy that binds our whole world together.